All right. Well, hey, this is a great turnout. Aloha and welcome. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy. One of the things I do is I put together these talks, and this month, we have Dr. Sarah Jaeggli, who I've known for a number of years, and we're really lucky to get her to come speak. I think you'll agree. Sarah did her undergraduate work at the University of Arizona, and then she came out to the University of Hawaii, where she got her PhD in astronomy. Her first postdoc was at Montana State University, and then she went to Goddard Space Center, where she was doing more solar work using satellites. And she was then hired by the Daniel K. Inouye Solar Telescope, which is being built here on Maui. And she is the instrument scientist for the DL-NIRS. That's the Diffraction Limited Near Infrared Spectral Polarimeter. And hopefully you have something about that, right?
Oh, just a little.
Just a little bit. Okay, good. Then I won't bore you because she's much more interesting to listen to. She's seen a total of 2 solar eclipses, and by seen, she means she's been there observing, taking data. She said she doesn't quite know if she's really seen them. And she's hoping to see the third on, I believe it's August 21st of 2017. So hope that a lot of us will see that, right?
Yeah.
All right. Well, let's give a nice Maui welcome to Sarah.
Thank you so much, and thanks, JD, for that nice introduction. So I'm supposed to be maximally annoyed here by this light. So, as JD said, I'm staff now at the National Solar Observatory. I do research, and I work on an instrument that's going to go in the Daniel K. Inouye telescope. But today I'm going to talk about some science that I've been doing. So I'll just jump right into it. When sunspots collide. Just a little? Okay. I didn't know. I see I have this light shining in my eye. I can't tell who's talking to me, so. Okay.
Sorry, folks.
All right. So I'll give you a little bit of an overview of my talk, what you'll be seeing. So I'll talk about how sunspots actually work to give you an idea of the science that I think is important. And I'll talk about how we actually measure the sun's magnetic field, as well as what is so important about sunspot collisions. Then I'll talk about a few weird things that happen to sunspot magnetic fields when sunspots collide, and what the Daniel K. Inouye telescope will do to revolutionize the study of sunspots. So what are sunspots? So this is the sunspot group I showed in the title slide, and we'll track it through its evolution. But I wanted to give you a little bit of an idea of the vocabulary that we use. I wanted to give you an idea of the vocabulary that we use to describe sunspots. So the very dark center of a sunspot is called the umbra, and it's surrounded by a slightly less dark, kind of filamentary penumbra, and we call these penumbral filaments. And umbras aren't completely uniform and black. They actually have little spots in them, and we call those umbral dots, little bright spots that occur in the umbra. And outside of sunspots, the solar surface is granulated, so we call these granules, and this occurs in what is the quiet sun, which is outside of sunspots and is fairly uniform and bright with this granulation pattern. There are also pores, these tiny little spots that you sometimes see scattered about large sunspot groups. So these are pores, like pores in your face. They're tiny little holes. And also light bridges. So these aren't actually bridges, but they are bright, and they cross across sunspot umbra. And down here is the Earth's scale. So these sunspots are quite a bit larger than the Earth, and they span a distance which is just gigantic as compared to the Earth. I'll talk about that in just in a second. I'll get to it. You're jumping the gun here. So the sun rotates, and sunspots rotate with the sun. You can also see that they evolve. So as the sun is rotating and time is moving forward, the sunspots are evolving. And this is a period of about 12 days, and it takes this big sunspot group those 12 days to rotate from one side of the sun all the way to the other side. And there's a few other little groups of sunspots that appear and then disappear, you can see. You also notice that the edge of the sun is a little bit darker and the center is a little bit brighter. And there's a sort of flickering that's going on in the middle that you can see. You might think it's the projector, but there's actually some flickering going on. So if we zoom in, there we go, and look at the sunspot group in detail, we can see a lot of different things going on. So sunspots are emerging and moving across the surface. They're combining into each other. They're pushing together. Some are moving away out into the quiet sun and then vanishing. And we get to the other edge of the sun. That's happening. And you also see this flickering pattern again, only it's a little bit higher resolution here. So this is the pattern of granulation changing, and it changes very quickly, much more quickly than the sunspots actually change. And again, here's the Earth to scale. I tried to make sure that was in all the slides so you could see it. So sunspots are dark because they're cool. So in the middle of a sunspot umbra, it reaches a temperature of about 4,000 degrees Kelvin or Celsius, which is about the equivalent of 6,700 degrees Fahrenheit. So that's still pretty hot. But in terms of the sun, that's pretty cool. And outside of sunspots, for comparison, the temperature is about 6,000 degrees Kelvin or 6,000 degrees Celsius and about 10,000 degrees Fahrenheit. It's not unfathomable, these temperatures. You can reach them in really, really hot ovens and furnaces that you use to melt metal or things like that. But it's still pretty hot compared to our surroundings, which are a very comfortable, 70 degrees or so. So I said that sunspots are dark because they are cool. Well, how does that happen? Hot things actually emit photon radiation. I'm pretty warm compared to the darkness of deep space. And I am actually radiating, and all of us are actually radiating photon emission. But it's photons that we can't see. They're infrared. But the hotter things get, the bluer the photons coming from them. And the hotter they are, the brighter they become. So this plot up here is sort of showing what happens when you take something like a piece of metal and increase the temperature of it gradually. So if we take a piece of metal and increase its temperature to about 3,000 degrees, it starts to emit invisible light. That's this section of the spectrum that we can see from blue to red. And if we heat it up a little bit more and more and more, the peak wavelength that it emits at shifts toward the left-hand side, which is toward bluer photons. And the total amplitude of the peak increases. And we here in Hawaii, we actually have a really good intuitive way to think about this. So we have lava. So the bright parts of lava are yellow here. And the cooler parts become red, and then they become black. So what's happening here is the bright yellow parts are over here on this side of they're emitting over here. They're hotter, so the peak here is shifted over to the left-hand side. And when you get cooler temperatures in the lava, they start emitting almost all in the infrared. So we're no longer seeing emission of invisible light from them. They're only emitting in the infrared, but they're still hot, of course, right? You would never never try and touch a piece of lava that was right next to this really hot section. So sunspots are cool because they have a strong magnetic field. So sunspots are dark because they're cool, and they're cool because of the magnetic field. So the magnetic field in a sunspot is about 3,000 Gauss. So we don't really have a good intuitive, Gauss is a unit of measurement for magnetic field strength, but we don't have a good intuitive idea of how many Gauss it takes to do certain kinds of work. But this number is 1,000 times stronger than the magnetic field at the surface of the Earth. So if you had a compass in a sunspot, and you tried to move the compass, it would resist you 1,000 times more than a compass on the Earth, or 10,000 times more. Sorry. So you basically wouldn't be able to turn the compass around because the compass needle would want to point in the direction of the sunspot's magnetic field. So how does the magnetic field make things cool? Well, if you can remember back to 8th grade, maybe, I don't know, maybe earlier, we know that energy travels by conduction, convection, and radiation. So conduction happens when I physically touch something, and the heat from my hand might flow into a cooler object, or something that's warm would flow into my hand and warm it up. So that's physically touching an object. We can change the temperature. Energy also gets transferred by convection. So if I heat up the floor of a room, the air at the floor will start to rise to the top of the ceiling. And that motion of the fluid of the air is convection. And also radiation. So like black body radiation I talked about earlier, hot things radiate. So radiation carries energy. And these processes happen inside the sun and at the surface and above the surface of the sun that we can see. So in the core of the sun, energy actually travels most efficiently by conduction. But atoms are really energetic and it's really dense, and they bump into each other, and that's the way they transfer their energy. So they physically touch each other and move energy from one atom to another. Now, when you move out of the core of the sun, just above it is the radiative zone. So photons travel through this radiative zone. So the energy is transferred by radiation all the way up to the convection zone. At this point, the solar atmosphere no longer can transfer. It's just become slightly cool enough that it becomes opaque, and photons get absorbed, and they can no longer transfer efficiently in this layer. So convection there takes over, and there's a conveyor belt from the lower layer of the convection zone up to the top, and hot material rises to the surface and cool material drops back down to the radiative zone to be heated again. So there's a cycle of convection that happens in this surface. And above the convection zone, this is actually the first layer of the sun that our eyes can see. The photons come streaming out again, and this zone is radiative. So the fact that the photosphere, which is the layer that our eyes can see, in the sun's atmosphere. The fact that it occurs right above the convection zone, and this is where sunspots grow, is quite important. So the sun is made of plasma, and plasma is charged, so there are free electrons streaming all around, and there are also ions which have lost their electrons streaming all around, in addition to neutral particles. And the sun is mostly hydrogen, that's these H's in here, and helium makes up most of the rest of the sun's mass. And so you have hydrogens, which some of them have lost their electrons, and free hydrogen ions wandering around in the sun's atmosphere. And plasma is charged, and it likes to travel along magnetic field lines. So when you enforce a magnetic field on a piece of plasma, the magnetic field has a strength and a direction, and this direction determines where the plasma will go. So if you have a hydrogen atom moving in the magnetic field, it will start spiraling around the magnetic field lines and eventually travel along the magnetic field line. So let's, can I do that again? There we go. So the ions and electrons will travel along the magnetic field lines. So this is really important for sunspots. So we have this convection zone and the photosphere. So convection is traveling up, it turns over, and then it goes back down. But if we enforce a magnetic field on convection, the cycle is broken. So the plasma can no longer turn over and go back down. So energy transfer is not as efficient where there is a vertical magnetic field in the sun's atmosphere, which is what happens in sunspots. So if the convection is broken, this plasma is still radiating, so it radiates away all of its energy. And that cools the section of the sun where the magnetic field is. So that's what makes a sunspot. And sunspots also grow at the base of magnetic loops. It's just not a magnetic field that's poking up randomly. It's actually connected to another end of the magnetic field. There we go. So how do we make a sunspot? Let's say we've got this magnetic field, which is lying in the convection zone underneath the surface of the sun. We can't see it. And here's the photosphere. So the magnetic field, the convection zone is really turbulent. So there's gas flowing up and down and all over the place. So the magnetic field gets perturbed, it gets disturbed, and it starts to undulate and become unstable. Then it starts to rise up to the surface. And as it goes up to the surface, it sort of expands. And outside of the surface, there's no longer the strong gas pressure which is inside the sun to confine the magnetic field. So it expands up over the surface and makes this huge set of loops. But down at the bottom, we have the strong magnetic field where the magnetic field passes pretty much vertically through the surface. And what this looks like is the magnetic field from a horseshoe magnet. So if we had a horseshoe magnet sitting underneath the surface of the sun, it would make a magnetic field sort of like this. So a horseshoe magnet has a north pole and a south pole, and very similarly, sunspots have north poles and south poles. They're not as uniform as a horseshoe magnet. They're not as normal. But nevertheless, they have north poles and south poles. So sunspots form at the base of these loops. I made some kind of weird looking squid here or something. But sunspots form at the base of these loops, and they have north poles and south poles. So now how do we measure that magnetic field that's in sunspots? Well, we do it by looking at atoms, and you'll say, atoms are really small, and the sun is really big, and even sunspots are really big. So how do we see these atoms? Well, atoms have a signature in the sun's spectrum. So this is a rainbow or a spectrum of the sun, and the colors have all been spread out, and you can see that there are very fine lines in this spectrum. And these are actually due to atoms. Things like calcium and hydrogen and magnesium and hydrogen again make some of these very strong lines. But if you zoom into a section of the spectrum, you can see that there are wider lines and there are even finer lines, and it just keeps going down. There's just all of like a forest of lines that you're seeing, and all of these little twigs, there's trees and twigs, so all of these little twigs are actually caused by things like nickel and iron and titanium. Of course, there's only a very small fraction of these heavy metals like nickel and iron in the sun, but they have such an impact on the light that we see from the sun. They're absorbing light, which is getting emitted from lower down in the sun's atmosphere. So a color here corresponds to the photon wavelength. And photon is a particle, but it's also a wave. And the wavelength is a measure of the distance that it takes a photon to wiggle once. So one peak and one trough. So if we measure that, that's the wavelength. And a typical wavelength for visible light from the blue to the red is about 400 to 700 nanometers. And a nanometer is about 100 times smaller than the standard width of someone's hair. So it's pretty small, but again, it's not unfathomably small. I can pull off my hair and try and split it 100 times. Yeah. Yeah, that's right. Well, it has an energy. And you can equate energy to mass. That's E equals mc squared, right? Yep. So you've got it. So these atoms in the sun's atmosphere make a signature. They make a dark line. And some of these lines are sensitive to the magnetic field. So if we look at a sunspot observation, like this one, this is from the Inouye Solar Optical Telescope Spectropolarimeter. It's a satellite which is in orbit around the Earth, and it was launched by the Japanese Space Agency. But the data is free to use, so I often use it. So this is a sunspot from that satellite that they've observed. And I can take a slice through this observation and look at the spectrum that they've taken. So this is the wavelength spread out here, just like in the last image. And this is the distance on the sun in the vertical direction. So each of these pixels in this direction corresponds to a different color, but I haven't colorized the spectrum here because I'm doing science. So the colors don't matter. I know what they are because I can assign them based on their wavelength. But you see that outside the sunspot, there are two lines, and these are two iron lines. So this is iron, which is in the sun. And when you go inside a sunspot, that's this dark section. So the entire spectrum is darker, but you also see that the lines split into 2 or 3 segments. So this one iron line splits a little bit, and this other iron line splits a lot more. So the line splitting is actually proportional to the magnetic field strength inside the sunspot. And we can use that to calculate what the magnetic field strength is. So we do that in the following way. We take our observation and we take a slice through this image. And I can plot this slice as brightness versus the wavelength. And it might look something like this. So we have these three components of the iron line. One is unshifted at the same wavelength, and the two others are shifted by the magnetic field. And I make a model of the sun. So I put in the magnetic field strength, just a best guess, a direction, and a temperature, and a velocity for the sun's surface. And do a calculation and come up with a profile that might look something like what I've observed. So that's this one. Has three components, looks kind of the same. And I compare those. So it turns out they're not actually the same. But I go back to my model and make changes and then do the calculation again. And eventually these things will come into good enough agreement that I'm satisfied. Say, okay, this is probably about what the magnetic field strength is, and this is the direction, and the temperature, and the velocity for that line. And it's really annoying to do this process by hand, but computers make it super easy. So I put my data into a computer, and it does all of the iterations between the model and my observation, and it comes up with a map for the sunspot of the magnetic field strength and the magnetic field direction. So remember, the direction of the magnetic field is like a north pole or a south pole. So the north pole is where the magnetic field is pointing up out of the sun, and the south pole is where it's pointing down into the sun. And that's what you're seeing here. So white is where it's pointing up, and black is where it's pointing down. And up here is the magnetic field strength. So this sort of looks like the intensity of the sunspot, but not quite. There's some differences. So this is the picture of the magnetic field strength. So now that we know all about sunspots and how to measure their magnetic fields, what happens when they actually collide? So, there we go. Oh no. There we go. So this is a movie of a different sunspot group than the one I showed earlier, but I think it's a good example to look at. So you see over on the left-hand side an image like what our eye would see on the sun's surface of a sunspot group emerging. It evolves and then almost disappears by the time it reaches the limb, which is what you see coming up over on this side. That's the edge of the sun. So it's rotating around to the backside of the surface of the sun. You can also see this is the magnetic field direction. So white is where the magnetic field is pointed up out of the surface, and black is where it's pointed down into the surface. And you probably noticed this little red arrow that I put in the movie. There's a thing that comes up, the opposite polarity that emerges inside of this black polarity. And it pushes through the edge of the sunspot penumbra, and then after it's almost all the way through, it vanishes quite suddenly. So this is actually a sunspot collision in progress. The opposite polarity here is crashing into the south polarity sunspot, and then it suddenly vanishes. And the reason it suddenly vanishes is going to be explained on the next slide, but I'll talk about first how to make a sunspot collision. So I talked about how sunspots emerge from inside the sun. So you have a magnetic loop that comes out of the surface. And things aren't always quite as nice as that perfect loop that comes out. Sometimes sunspot magnetic fields are quite complicated, and you can imagine that this is because the magnetic field wiggles up and down through the surface and creates north and south poles in close proximity to each other. and it just passes up and down through the surface like a sea serpent. So that's one way you can make a sunspot collide, is by just having a really complicated magnetic field in your sunspot group. Another way to make sunspots collide is to crash a new group into an old group from the bottom. So if we have our original loop and we emerge flux from underneath, we emerge the magnetic field from underneath the sun's surface and crash it in that direction, we can get north and south poles in close proximity to one another. And kind of similarly, we can crash two sunspot groups in from the side while they're already on the surface. So they both emerge, and then they crash into each other as they're evolving. Where are they going to go? There we go. So they crash into each other as they're moving around and doing their thing, living out their lives. We get the north and south poles in close proximity to each other again. So why is this important? Why does having a north and a south pole magnetic field next to each other cause interesting things? So it turns out that flares happen in these kinds of groups, which are complex. Almost all of the extreme flares on the sun occur in complex sunspot groups where you have north and south polarity sunspots in close proximity to one another. So flares happen, solar flares, of course. They happen when energy stored in the magnetic field is suddenly released. The magnetic field snaps, and then it rearranges itself, and then it quiets back down. So I can show the movie here. This is of an extreme flare that happens in this sunspot group. And this image is actually from an ultraviolet telescope. So we're seeing material which is really hot, and it's also a little bit higher than the visible surface of the sun that we can see with our eyes. It also lets us see material which extends much further above the surface, which is what we're seeing here. So you see bright emission, which is the hallmark of solar flares. And there's a little bit of material which is ejected that's called a coronal mass ejection. And that's important because it can affect us here on Earth if it comes in our direction. So flares release energy equivalent to 1 million nuclear bombs. I have also heard it said that a flare of this size could power the United States for 1 million years or something like that. I mean, they're just enormous amounts of energy. And it's a good thing they're really far away. Because we don't really experience much of a consequence from these brightenings on the sun. But the material and the particles and the magnetic field that comes off of the sun from these kinds of events can affect us. It affects our electronics. It can affect the health of astronauts who are in the space station, and also satellites in orbit. It can cause disruptions of power grids and all kinds of interesting things. But you need a really big flare to cause serious problems. And most of the time, well, this kind of event is just about the most powerful that we typically see. So the sunspot underneath this ultraviolet radiation that you see here is actually quite complicated. So you can see here there's black and white polarities which correspond to the north and south pole, and it's all mixed up. So that's important. And this is from a sunspot collision. And so I'll get back to this group. This is a really interesting one. I really like it a lot. I think it's just a beautiful image too. So during sunspot collisions, other weird things happen besides flares. So really weird things happen to the magnetic fields. I already talked about how magnetic fields are the reason sunspots are dark and cool, and how they point vertically out of the sun's surface. But it seems to be an exception to the rule when sunspots collide. So we can look now at the magnetic field that we get for this sunspot group. And you see there was a sunspot here, and there was a group or chain of sunspots that went up in this direction. But there's this really weird thing going on right here. The sunspot magnetic field is really intense there for some reason, and we're not quite sure why that is. So I'll circle that, and if we look at the direction of the magnetic field, so this is now showing the north poles and the south poles for this sunspot group. There's one sunspot here, and then this other main sunspot plus the chain that's extending off to the right. And then this region in here is where we saw that really intense magnetic field. So it's actually above a place where the north and south poles are turning over. So the magnetic field here is actually horizontal, it's not vertical. So the vertical magnetic field is coming from this part of the sunspot, and then it's going down into that part of the sunspot. And this is a place where the field is actually horizontal. So we can assign all of these polarities. Oops. Oh yeah. So if we take all those polarities and map them out onto this image, we can see which sunspots have which polarities. So there's a south pole and a south pole here and a south pole there and up here and there and there. And then the north poles, here, here, and these two right here are also north poles. So this very strong magnetic field, which is strange, is coming in between this sunspot group and this larger sunspot here. So this is caused by a collision, actually. It's not this sunspot which is colliding into this one, but the smaller group which popped up and moved over into this sunspot. So this thing was caused by the collision, and it has something to do with flares in a sunspot. We're not quite sure what it is yet. So I've written a paper or two about this. And if you want some really dry bedtime reading, go look those up. And I also wanted to figure out what the overall classification of complex sunspots was. So how many complex sunspots actually occurred during the past couple of solar cycles from 1992 to 2015. And I figured that out as well. And this one's a lot shorter and easier to read. So if you want to look that one up, it's good too. So I said sunspots were dark because they're cool. And they're cool because they have a strong magnetic field. But the existence of these really strong magnetic fields in between the sunspots that have collided breaks our theory about how sunspot magnetic fields should really work. And as I said, these are related to solar flares in some way, but we're not quite sure what it is yet. It may be that these really strong magnetic fields are storing energy in preparation for a flare, or they may be a manifestation of the magnetic field after a flare has occurred. So a lot more work is necessary. And that's where the Daniel K. Inouye telescope comes in. There we go. So the Daniel K. Inouye telescope is going to revolutionize the work that I do with sunspots. So maybe you've been up to the summit recently. This is what it looks like. So that telescope is dekissed, as we call it. And it's going to be ready for operations in spring of 2019. Pretty soon. Only have a couple of years to prepare for it, and there's a lot of work to be done still. The dome is finished, but it's completely empty on the inside. Well, not completely empty. There's things going on. But the telescope isn't in there yet, and none of the instruments are there yet. So it's going to be, when it comes online, the world's most advanced solar telescope. And I could actually cross out solar and just say telescope, because there are a few other telescopes which are almost as complicated. but we're definitely in the running for most complicated telescope and most advanced. There's a lot of new technologies which we're trying out in this telescope, and it's because it's so big. It's a 4-meter mirror, and that collects so much sunlight that we have to deal with it. It's going to get hot, and there's just so many different technologies which have to come in and help us deal with how much sunlight we're going to have. And it's also going to be very high resolution. That's what the 4-meter mirror is for. High speed as well, and high sensitivity. So these are all important when we're looking at sunspots. But I'll just talk about the high resolution just for now. So DKIST will allow us to see the smallest scales on the sun that we've ever seen before. So this is a satellite image of Hawaii, and I've taken it and I've degraded the resolution down to what is currently the equivalent of the scale that we can see on the sun, which is about 100 kilometers. So if you look at the satellite image at 100 kilometers resolution, you can't tell that Hawaii is there at all. It's just sort of a green smudge against the clouds, and you probably wouldn't notice it. But at the resolution that DKIST will be able to observe, 20 kilometers, you can tell that it's an island chain, in fact. You may think it's still not very good, but compare that to the entire Earth. You know, Hawaii is pretty small, might fill in this box here. And if we take this scale Earth image and consider that scale on the sun, we're going to be seeing a tiny, tiny blip in here, which is the size of the Big Island on the sun. So it's just going to be amazing. So that's really important for these things. It turns out that these are actually better described not by one magnetic field, but by two, or at least two. So that means that there's a magnetic field next to another region with a very different magnetic field, or they're on top of each other. And our new solar telescope will allow us to differentiate between those two situations. So we'll be able to figure out in detail what's going on in these sunspot collisions. And we'll also be able to see both high resolution, spatial resolution, and temporal resolution. So we'll be able to take observations very rapidly to see how the magnetic field changes during flares, and also at high sensitivity. So we'll be able to detect very, very small changes in the sun's magnetic field. So we will know more about these regions, and probably more about solar flares and the magnetic fields which drive them from beneath the solar surface. And there we go. Thank you. And are there any questions? I can't see any of you, so. People try and make predictions, but they're often proven wrong. So during the last, before the last solar cycle started, there were a couple of different predictions of how much how high the activity level would be, basically the number of sunspots that would be in the solar cycle as a function of time. And both of them were wrong. Oh, right. Yeah. Yeah, you have a question? Yeah, so the question is why sunspots are only found in the equatorial area of the sun. And they're actually, they occur in specific activity belts, not just at the equator. The activity belt start at about 45 degrees up in solar latitude, is that right? Yeah, latitude. And so at the very beginning of the solar cycle, the sunspots occur at very high latitudes, almost 45 degrees. And then as the solar cycle progresses, they travel down to the equator. So those activity belts migrate toward the equator, and that has to do with the solar dynamo. The plasma in the sun is rotating, and that actually generates a magnetic field. It generates the magnetic field which eventually drives sunspots. But the dynamo has to wind up. So you can imagine as it winds up, it sort of migrates slowly downward toward the equator. And a question over here? So the question is, two things, sort of, how long, or does it actually take a really long time for for photons to get out from the solar core? And then can we see quantum tunneling effects in sunspots or in sunspots in general? So it does take a really long time for photons to get out of the solar core. It's a basic calculation that every grad student does when they're starting as PhD astronomers. So you do the path length calculation. So photons basically get emitted and absorbed so many times as they go from the core out through the radiative zone to the convective zone. And then it basically takes 0 time for them to go through the convective zone and up to the surface. So yeah, that does take something like 1 million years. I'm not quite sure about quantum tunneling effects and how or if we will be able to see them with the telescope. But I think the answer is no. Yeah. And we had a question from online? No, you didn't. Question over here? That's what we're supposed to say. So, there are several websites online where you can go look at an interactive map of the solar eclipse, and pick out where you want to go. There's a lot of recommendations about weather along the eclipse path. There's a website served by Goddard Space Flight Center, which is excellent, and it shows you basically all of the solar eclipses that are occurring. And for advice in actually viewing the solar eclipse, we're supposed to say that any looking at the sun is going to damage your eyes. It's good to be careful. There are eclipse glasses that you can get to view the sun safely, and those are basically a really, really strong filter. So you hold them over your eyes, and then you can look up at the sun and see what's going on. During totality, it is safe to remove those eclipse glasses. But you have to be careful because totality begins and ends, and you can end up looking at the sun when the sun comes back out again, and that's bad. But it's good to be careful and find an expert, your local amateur astronomer. They're always a good bet. So there are probably many amateur groups getting together along the eclipse path. So if you find one of those, they should have some good recommendations for viewing safely. And you had a question? They have to be pointed in the right. Well, solar flares, in order to affect the Earth, have to be pointed in the right direction in order to affect us. Yes. Absolutely. Yeah. So there are many recorded solar flares and how they affect the Earth. Um, we see uh, aurora, which come from the interaction of the sun's magnetic field and charged particles coming from the sun during a solar flare, and the Earth's magnetic field. So the charged particles enter the magnetic field lines around the Earth, and then they come down and hit the Earth's atmosphere. So we see aurora very frequently. Well, not down here, but up around the poles, Norway, Sweden, they see aurora on a regular basis during high levels of solar activity. Did I cover most of your question? Sort of. Oh, if solar flares have ever affected life on the Earth. Well, besides, there's sort of indirect evidence for changes in the atmospheric chemistry of the Earth. So historically, we notice that long-term high levels of solar activity do have an impact on the atmospheric chemistry. Yeah. Yes, I believe that's right. During the 70s, a CME did knock out part of the Canadian power grid. There are several other examples. One of the most famous examples is the 1859 Carrington event flare, which was just a massive sunspot group that produced a series of very intense flares which headed straight toward the Earth, and it caused currents to run along telegraph lines. And at the ends of the telegraph lines, they sparked, and of course telegraph stations have all this paper lying around, so they just burned to the ground. So all the telegraph stations needed to be rebuilt after that. But there were that was the first visible light flare that anyone had seen. Oh, sure. So the question is, how often do I look at the mathematical representation of the magnetic field of the sun as opposed to just observationally? And I mostly look at it observationally. But there are scientists in my field who do all of the calculations for determining the magnetic fields from first principles and how they're actually generated. So other people do it. I don't usually, but sometimes. Let me just go back to that. So we're talking about the spectrum that I had with the rainbow. Let me exit out of here and go to it faster. This one. Okay. Yeah. Yeah. So why does hydrogen, although Yeah, so why does hydrogen have three separate lines, three separate places where it absorbs in the spectrum? So it doesn't have to do particularly with the atom itself, but the energy levels inside of the atom. So the hydrogen has one electron, and it's actually pretty easy to calculate the energy levels that that electron can take inside the atom. So these different spectral lines of hydrogen are caused by those different energy levels. Yeah. Yeah. So similarly, calcium actually makes many more lines, and as well as magnesium and nickel and iron and titanium make so many because they have so many possible places where the electrons can be. Yeah. Yeah, well that's excellent. So, you had a question? The magnetic field does. How does that work? Yeah. So this phenomenon is called the Zeeman effect. So the question was, how does the magnetic field actually split the energy levels in the atom to cause separate spectral lines? So this is actually called the Zeeman effect, and you can look it up. It's discovered by a Dutch physicist, Peter Zeeman. And he basically did the experiment where he put a light source, which produced emission lines like these, only bright instead of dark. And so he put that light source into a magnetic field and cranked the magnetic field strength all the way up. And he actually saw the splitting of these energy levels. And this is because he found out later, he did the theory, that when the magnetic field outside the atom is comparable to the magnetic field inside the atom, that causes a coupling between them. It actually raises a degeneracy in the level. So this is a quantum physics thing. So you have energy levels which are lying on top of each other for the most part. So they would always occur at the same place, but the magnetic field causes that degeneracy to lift. So the energy levels are allowed to have slightly different values. And the question in the back? So the question is, what are solar scientists doing to help convince legislators to protect the energy grid from solar flares and the effects of solar flares? I personally am not doing quite as much as I should be. Folks at NASA and at the National Science Foundation do make sure that our legislators are aware that these are issues, that solar flares can happen at any time, and the consequences can be dramatic. As to what kinds of changes can be made to the power grid, whether those are simple or difficult, I know one of them is that power transformers are quite unique pieces of electronics, and they're complicated to make, and we don't have any spares. So that's one thing that we can convince our legislators to change, is increase our reserve of transformers and make sure that they're interchangeable between different power stations. And I know maybe you have another question, but did anyone else have you had a question? Yeah, that one is Hinode. Uh, well, this is also Hinode as well. So so yeah. I know I should repeat your question, but let's see. So the image that I showed of my sunspot originally from the beginning of the presentation, I'll go back to it. Is from Hinode. And what makes Hinode special or different from other telescopes? Well, as you said, Hinode does look at a small field of view. This particular imager on the telescope looks at, I think, the smallest field of view of any of the instruments on that particular satellite. And it's not able to see the whole disk at once. So it can't image the whole sun at once. But the thing that makes it really handy is that since it's in space, we don't have the Earth's atmosphere in the way. So the Earth's atmosphere can cause jitter, and it's something we're working really hard on for the Daniel K. Inouye telescope is the adaptive optics system, which will stabilize the images and give us really clear resolution of the surface. But since Hinode is in space, you never have to worry about that step. But it requires that, being in space, it limits the size of the telescope you can put up. So we can never reach the possible resolution that the Daniel K. Inouye telescope will have with a space-based telescope. A question in the back there? So, does it become finer? Or what's the smallest scale? Yeah. Oh, yeah. So it basically does solar granulation appear finer and finer as you increase your resolution? And we think that's actually not the case. There is a limiting size on structures that appear in the sun. And with the Daniel K. Inouye telescope again, we can resolve that scale. We think we can. We're not quite sure. We're trying to see if theory and observations match for that. Yeah, in the back. What depth are they? Let's see. So you said that these granules are about the size of Texas, and I think that's correct. That's about right. And how deep they extend, I think about several times as they are wide. So the granules extend further down, several times wider or longer than they are wide. But you can look at different scales of granulation. This is actually the smallest scale of granulation, but you can actually see larger scales in the sun. Actually, when you look at the velocity, you see the solar surface lifting up and relaxing. And that shows us much larger scales of granulation, which are perhaps as large as a sunspot. And those modes of granulation actually extend deeper into the solar atmosphere, all the way down to the bottom of the convection zone. Yeah. Or mirror or lens? So the question is when the mirror is being delivered, and I don't actually know. It's going to be exciting for me too. I don't know if they actually need to widen the Haleakala highway. But they will have to close the highway that day. And the Crater Road maybe need to widen? Yeah, I'm not sure. No. And behind you? Yeah. Yeah. So the question is, how long during the day will we be able to observe with our solar telescope? Um, on Haleakala, conditions are really good in the morning, and when you look up at the summit, you can generally see all the way up there and see the telescopes. Um, but clouds come in the afternoon, so we expect that after about lunchtime, we probably won't be able to observe. So it depends on the weather conditions. If we can observe all day, we will. But depends on the clouds. In the middle there? Yeah. So how will we get rid of the heat from the main mirror of DKIST? And that's a big problem that a lot of really smart people are working on. Basically, there's a couple of different ways we're trying to mitigate heat. There's first at the prime focus, a heat stop. It's an aperture stop, so it cuts off the edges of the light and rejects all of the stuff that's coming in from the sides. So it only lets a narrow beam of light go through. And at the secondary mirror, that mirror is actively cooled. It's basically like a fire hose on the backside of it, pumping coolant through and then away back down to be cooled again. So it's just it's going to be exciting to see. Yeah. There are some emergency mitigation measures in case something doesn't work. Maybe a bug lands on the secondary mirror, or we point the telescope the wrong way. The dome will immediately shut. The telescope will slew away, and there's all kinds of emergency measures that are in place to make sure we don't melt any part of our telescope or harm people. Or yeah, it's a huge problem. And another question there in the back. Yeah. So your question is basically for stars and planets, how does the magnetic field get generated? Yeah. So in the Earth, we know that the Earth has a molten core of iron. It's spinning. So that spinning motion generates a magnetic field. Something like Mars or Mercury, all they used to have a molten core, but now it's solidified, and they have a weak magnetic field. The Jupiter and the Sun are actually quite similar in the fact that they have plasma circulating around because they're rotating, and they're not rigid bodies, they're fluid. So you get differential rotation. So it actually needs to rotate faster at the outside than at the inside. So this differential rotation is actually one of the causes, coupled with the convection that happens inside the sun, which generates the magnetic field. So it's the swirling plasma that generates a magnetic field. That's a good question. So I just talked about how the swirling plasma in the sun generates a field. But the question is now, does convection make its own magnetic field? And it does. It's called Magneto Convection. So the convective cells, since they're circulating up and down, actually do generate their own magnetic fields, very small, weak ones. But it's been proven that even without the internal dynamo of the sun, you can generate magnetic fields just with the convection. Yeah, you have a question? Oh, so do the fields line up with the convective cells or up and down? Yeah. Yeah. So yeah, that's right. So because the convective cells are circulating up and down, the field that they generate is perpendicular. I haven't really thought about it, but what the results that I've seen are very chaotic. So you get magnetic fields. They might start out horizontal and lined up, but very quickly, because of the turbulence of the convective process, they start pointing in all different directions. And basically, the magnetic field that gets generated by the plasma also gets carried along by plasma because it's charged. So there's an interplay between the magnetic fields that get generated and how the gas moves. And a question here in the middle. Yeah. Thanks a lot. You guys have been great. Thank you.